What the heck?
Tagon.
Real quick, it's time for
Monday Math Nuggets.
yeah. And today we're going to be doing the, what the hell am I doing today? The inscribed angle, no, I already did that. The Intersecting Chords Theorem. That's what we're going to be doing, and it's one of my favorite geometric facts. It's very quick, it is indeed a little nugget, and so we will be doing that today. So, the inscribed angle theorem is a lovely statement about circles. I keep saying inscribed angle theorem. The intersecting chords theorem is a beautiful statement about the geometry of circles. It simply states that if you have a circle and two chords inside that circle, which intersect, as per this name, intersecting chords theorem, and you focus in on the lengths on either side of the intersection point for both chords, and say we label them A, B, C, and D, it is a true fact that A times B is equal to C times D. Every time, forever and always. It's a beautiful, beautiful statement. So let's prove it. It's quite easy. We can prove it very quickly. All we need to do is adjust our drawing a little bit so I can actually draw these line segments that I need to draw. So this one is B, this one is C, this one is D, and this one is A. So now we need these line segments which connect those two things together, and we have ourselves two triangles. Now, what else did I prove that I've accidentally been calling this video like 3 times now? I've also proven the inscribed angle theorem, which tells us that if we have some central angle that subtends 2 points, then any point along the major arc that's connected by those 2 points, if you inscribe an angle on it, that angle will always be half of the central angle that subtends this arc here. Which means both of these angles are half of whatever central angle this is, which means that they must be the same. Right? Those angles have to be the same. Likewise, this is some central angle, and these are both inscribed angles on the major arc between the 2 points, which means these angles must be the same. And if you don't have to say it, but if you want to, we also have vertical angles here, so those angles must be the same. That means that these two triangles are similar triangles every time. No matter which two intersecting chords you have, they will always be similar triangles. And because they are similar triangles, that must mean that they are scaled up versions. One is a scaled up or down version of the other one, which means that the sides that correspond to each other are some constant multiple of one another. We can tell which sides correspond because it's the ones that are opposite the same side. So A is opposite the one-notched angle, and we know that D times some number K will give us A, right? So we know that D is equal to some number K times A. B and C are both opposite the two-notched angles, which are the same, which means that C is then also equal to that constant times A. I'm sorry, constant times B. I apologize. I switched those around. My mistake. So we see that because B and C are both opposite the double-notched angles, they must be corresponding sides, and so we have that B is equal to K times C, right? Clear as day. And now all we have to do is multiply these two things together, right? We're going to multiply, I'm going to write them in the opposite order. I'm going to write KC equals B, because now when we multiply the left sides, we get K times C times D, and when we multiply the right sides, we get K times A times B. And that constant K is irrelevant, and we're left with the fact that I claimed. Intersecting chords have this amazing property that the lengths on either side of the intersection in one chord, when multiplied together, give you the same number as when you take the lengths on opposite sides of the other chord and multiply them together. A beautiful fact. Thank you very much for watching.